Amy's arrived. Hello YouTube, and this is my latest circuit board design, Amy version number 2. So this is an expansion of my original battery protection circuit, but it's going to be designed for lithium iron phosphate batteries, or really any battery chemistry, because it's going to have a Raspberry Pi Pico on here, so it's completely programmable. So the boards have just arrived from JLC PCB, not a channel sponsor, which they were. And all the markers on here, what they do. So you're going to have your input power, this end, so that also monitors the voltage coming in, and then you've got your cutoff for your battery, so you can have different loads. So you can have 2 loads on here, and you can cut them off as the batteries get low. You've also got an indicator LED up here to tell you status. That's the rear side of the board, designed by me. So just got to solder on the Pico and get it all programmed and running. So I've got my Pico, got my items in the breadboard, just got to move them over onto here. So to make life easy, always start with the smallest components first. So I've already soldered on this LED. Going to do this little SOT 32 package, then the resistors, then the Pico, then the DC-DC converter, then the relay. That way the big blocky heavier things don't get in the way. For instance, if I put the DC-DC converter on now, it'd be a bit trickier to solder these pads. Not so bad for this board because then it's quite well spaced out, but if you've got a denser board, it becomes a real issue. And there it is, all soldered up. So quite easy to solder the Pi to a PCB, just castellated edges. So it's the hardest bit is lining it up with all the pads, because of course it's quite easy to get the angle wrong, and you've got to get it lined up this side. But the idea is you just tack one corner, it gives you a little bit of movement in the solder. Tack the other corner when it's all lined up, reflow that joint that you had because you put it under stress, and then just reflow all the joints, and you should get a nice fillet of solder down the edge of the PCB like that. And that's how you use a Pico in a board. That's if you want to surface mount it, obviously. You can always do it through a hole. And yeah, so all you need to do is throw some software on it and see if it works. So I'll take you through the software now.
And the code we got running on here is written in Python as Pico code. I've defined all the relays and the LEDs and stuff on here, and the ADCs are all self-defined. And all we're really doing is, this is our loop command, is we're basically checking the voltage on that resistor divider input pin, having a bit of a time to take bit, and then if the voltage is above a threshold, we set the pixel a particular colour and then set the relays on or off accordingly. Now what we've got here as well is we've got some delays in, so we've got these states, these variables, relay on, relay off. So we basically just set the states, and the reason we do that is so we only blip the relay. We don't hold the relay in one position because it's a setting relay, so we just need to blip the relay over to one state. So this is why we can have this command here and this command here. So if the relay is in an on state, we blip it, then we go to sleep, and we blip it low again, and it stays low because we only need to set the relay once. And the same, that's relay off, set the relay on, set the relay the opposite direction, and then we set it off again, and it stays off. So the relay is only ever powered in these times here when it sees there's been a change to them variables, and the change only occurs if we deviate out of these ranges. So we actually only set the relay on, relay off there. This is the only one we set the relay on. So what this is dependent on is the ADC values, knowing what these are going to be. So these aren't set yet, these are just random values I've picked, hence why they're nice round numbers. But we've got a calibration routine that will run first. This is the calibration routine, and again we've got the same states just to set the board up. And all we're doing here is we do some bit of nice flashing of the LED to show you what state we're using for defining the value in the register, if that makes sense. So we read the ADC, I'll show you here. So we read the ADC, call it voltage. Voltage is our data. we then split that number, so you'll get a 6-digit number of something. So you'll get something like that, for instance. Then what we'll do, we'll go the first digit of that will be 0. Second digit will be 0. Third digit will be 0. I've used a really bad number here. That digit will be 5. That digit will be 6. So we've taken that number, which is what we get from our ADC, and we put it into this sort of sequence. Then we can look at data 0 and pulse it that number of times. So this is why it's such a bad example. If this was 1, we would pulse the LED 1 time. And that way we can look at the colours of the LEDs and work out what value the ADC is telling us. So we can run this program connected to a voltage source at our cutoff voltage that we want to use, count the flashes of the LED in different colours, and then we can apply that into this program to give us these values here for the cutoffs that we want to use at certain voltages. And that's how we can program it. Now I've got this split into 2 programs. You could probably you could quite easily make it 1 program, and you can hold a pin up high to get into calibration mode, but I'm lazy, I haven't done that, and this is fairly quick and dirty just to see if this thing works. So I'll show you what them programs do now.
So the board is programmed now, and it's now connected to a power supply. And what I want to do, I want to set it to a cutoff voltage of 23 volts, which will give me a cutoff voltage of around 2.9 volts per cell, because I've got an 8-cell pack. Now what this will do, it will read the value of the ADC and output it to the RGB LED, and then it will flash the number of times that value is in the register, as in the code. So you start off with red, green, blue, pink, yellow. So all we've got to do is count the amount of times it flashes red, green, blue, and then that will give us the reverse value of what's in the register. So we'll also set the input voltage to 23.0, and that is, come on, like that. Turn it on, it will go through a relay check, so the relay will click on, it'll flash red, green, blue, pink, yellow to remind you of the colours. Relay will click off to check that's working, and then it will start counting the register values. So we've got red, green, blue, pink, yellow, and it will flash 1, 2, 3, 4, well, 1. Oh, I need to think hard and count. Right. I could just watch this video and then play it back. That could be easier. Pink. And then yellow. So that is what's the values in the register. Did you get it? Right, so after letting this run for a little while at 23 volts, these are the readings I get. So these readings are always the same, stable. So that's why I've written them down once. These are the readings that are always changing. So red changes all the time because it's the least significant digit, because you've got to remember this is reversed. Green, it moves around a bit. That is between 6 and 7, so I put it at 7. It's just happy at 7 more. So the last number I got, which was fairly stable, was 27. So you get 0, because I don't care about the red one because it's moving around too much. 2794. You flip it round, it becomes 49720. So that's the cutoff value we'll have in the register in the program. And then we've got to choose a middle and a high end. So I don't know, 25 and 27 volts or something along them lines. No, that's too high. Do 24.9, 24.5, and something like that. Anyway, I'll work some numbers out, and then I'll put the list down here. Right, so we have our numbers. So for our cutoff voltage of 23 volts, it's 49720. Midpoint, I've chosen 24.5 volts, 52828. And at 26 volts being our high point, 56100. And that's our ADC values. All we've got to do is modify the normal main code, and that'll give us the voltages it will run at. So all I've got to do is modify the Python program, and program it back in. Simple. So the board is now programmed, and I've got it sitting here at 26.6 volts. So we're simulating what would be like if it's on a battery pack, and you see it's only drawing 7 milliamps, so it's a nice low current draw, and that's with the LED on. So as the battery gets flat and the power goes down, when you get to 24.5 volts, we should see, there you go, the LED has changed to red to let you know the battery's getting low. I think I need to play with these colours, because maybe that should be blue and the top end should be green, and then when it's getting near cut off it goes red. But I can change that, it's just software. And as it goes down to 23 volts, it should cut off. So listen for the relay click. There you go, the relay's clicked, the LED's gone really dimly red, dimly if that's a word, and you see you're still drawing 7 milliamps. So that's working. And then as the voltage goes up to 23 volts, it should recover. There we go. Oh, that's just a bit of noise. That's interesting. Okay, maybe we can play with the software so that we can have it so it recovers at a higher voltage. But that's the basic idea of it. So as your battery gets low, you would have your load. So I would have, say, my Raspberry Pi aircraft tracker and other things on the end of this relay, and then it would switch them off as the batteries get low, and that will save the BMS from tripping. So that's the general idea. I'm going to work on this a bit more, improve the software a bit. If anyone's interested, I've got some of these spare boards, so I can always ship some out. So let me know. I'll work on a site or something, or put them on eBay or something like that. But for now, if you just leave a comment, I'm sure we can get in contact. But yeah, I'll carry on working with this. But for now, see you later, and have a nice day. Bye.